Eval results are useless if they sit in CSV files. DuckDB lets you slice failures with SQL and find which prompt or model actually regressed. This is the setup you'll be able to run after this, which loads eval runs and flags regressions by grouping failures across prompt, model, and dataset. I'm Professor Pine, teaching AI engineering and LLM systems with simple Python. Most teams run model comparisons and end up with folders of CSVs. That creates a new problem. You can open a spreadsheet and stare at 1,000 rows, or you can ask a simple question with SQL. Success means fast triage. It means finding the prompt, dataset, or model version that actually caused the drop, without building a web dashboard or clicking through files. DuckDB is a tiny analytical database that runs inside Python. It reads CSVs and keeps everything in memory or in a single file. For evals, that makes it easy to store run metadata and query slices with familiar SQL. The payoff is a repeatable, scriptable way to flag regressions after every run. You get counts, deltas, and error breakdowns in seconds instead of hours. Conceptually, we will treat eval rows as structured events. Each row says which version ran, what model was used, which dataset and question, and whether the answer was correct. From there, we can compute accuracy per version, compare versions, and find the biggest drops. That pattern maps straight to SQL grouping, joining, and ordering. It is robust and scales to tens of thousands of rows without extra infra. We will build a small, reproducible workflow. You will create an Evals table, insert a few toy rows, compute the worst version, compare prompt variants, add new failures, and then detect dataset regressions automatically. No dashboard, just queries you can run in a CI job or a quick script before you ship. Now, we start by preparing the table and checking readiness. Now we create the table and verify it. This snippet creates an empty evals table in DuckDB and verifies readiness. It imports DuckDB, opens a fast in-memory connection with duckdb.connect, and defines a compact schema using con.execute. The columns track version, model, dataset, question ID, a correctness flag, and an error type so failures are easy to slice later. Establishing the table up front keeps subsequent inserts and queries reproducible and comparable across runs. A quick select count against evals confirms the table exists and that we start from a clean slate. If you prefer persistence, connect to a file path to keep results between sessions. The printed row count confirms the table was created and is empty. Next, we load some toy eval rows and surface the worst version by failures. This example loads toy eval rows and surfaces the worst version by failures. It inserts 6 compact records into evals with a single insert statement via con.execute for clarity and reproducibility. Each row records version, model, dataset, question ID, a correctness flag, and an error, matching the basic shape of LLM eval exports. The query calculates failure rate per version by averaging a case expression that maps failures to 1 and passes to DuckDB's round for readable percentages. Order by includes a version tiebreaker to keep results deterministic across identical rates. The printed worst version and failure rate show where failures concentrate right now. Now we compare prompt variants by dataset to find where the biggest change happened. This code compares prompt variants by dataset and highlights the biggest change. It sets the model filter M, then uses a DuckDB CTE named ACK to compute per dataset accuracy per version with avig on the OK column. Joining V1 with V2 aligns metrics and produces a delta for each dataset. rounded for readability. Ordering by ABS of the delta ranks both improvements and regressions by magnitude. So investigation targets pop out immediately. If you change M to another model, the slice updates and the selected dataset may differ accordingly. The printed dataset and delta reveal the most impactful change between versions. Next, we simulate a new run with fresh errors and rank error types for a chosen version. This example adds fresh failures and ranks error types for a chosen version. It inserts 2 additional v2 trivia mistakes to simulate a new run finishing or late arriving results. The variable cell_ver picks which version to summarize and is bound as a parameter to con.execute for safe, repeatable filtering. Grouping by error and ordering by the count, then by name, yields a stable top contributor to failures. Increasing inserted rows will shift which error leads, helping you focus triage on the dominant cause without building a dashboard. The printed top error v2 and count identify the most common failure cause now. Now, we run a regression detection query that finds dataset level drops between versions. This snippet detects dataset level regressions between versions without a dashboard. A DuckDB CTE computes accuracy per dataset and version, and a self-join aligns v1 with v2 for direct comparison. The where clause filters to negative movements only, while order by drop surfaces the worst regression first. Because it queries the same evals table you update during experiments, this check is fast to run after every batch and simple to automate in CI. You can easily extend the query with additional filters, like a specific model, dataset family, or label. The printed regression dataset and drop quantify the biggest backward step to fix. In a real pipeline, this maps to a nightly job. You insert fresh eval rows at the end of each run, and then run the few SQL checks we used. The queries are the same, whether you have 10 rows or 10,000 rows. The only change is storage mode. In memory for quick tests, file backed for persistence across runs. Recap: it is a small DuckDB-based eval table, plus a few targeted SQL queries. Use it when you want fast, scriptable failure triage without building a dashboard. One caveat: you need disciplined row shapes and versioning so diffs are meaningful. Next step: add a minimum sample threshold so you only alert on regressions that affect at least a given number of questions. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.